Hi there, welcome to part 2 for our lessons on periodic functions. In the last lesson we looked at what a periodic function is, and they are functions that have a cyclical nature, they repeat. And we ended by looking at the sine curve and how it's produced by going around a unit circle, spinning all kinds of angles, for example angle of 120, and then finding the vertical height. And then the collection of all those vertical heights is your sine curve. So 120, for example, is here, that height is right here, and as you follow all the angles, you create this thing called a sine curve. There's our sine curve. It's one of the most important periodic functions, and in this lesson we're going to go a little bit further with it. So let's take a look. So here we have a unit circle. We know a unit circle has a radius of 1, so you can see in every direction here there's a distance of 1, and also if you drew a diagonal radius it'd also be 1. So let's say we put a random point on the unit circle and we want to know the location of that point. In other words, we want to know the x and y coordinates. We want to know what is the x value and what is the y value at that point. Okay, to find those x and y values, we can draw a triangle, and that's what we were doing in the last lesson. And in that triangle, we can use basic trigonometry. We can say, hey, if we know this angle here, we can find the x and y values, right? We can find this distance and this distance by using basic trig. So first of all, we began with saying, okay, we know the radius is 1 because it's a unit circle. So if we set up a sine ratio in this right triangle, we can do opposite over hypotenuse, which is y over 1. So that would be the sine of the angle. But since this distance is 1, since the hypotenuse is 1, we can just say sine theta equals y, or y equals sine theta. So if we want to know this distance, we call it the vertical distance, or in other words, the y-coordinate of this point, we can just do sine of theta. So what about looking for the x value? Okay, we can use the cosine ratio. We can say cosine of this angle is adjacent side over hypotenuse. So cosine of the angle is x over 1, using basic trig. Now looking at this, again, since the hypotenuse is 1, this value of 1 is irrelevant, and then we know that x equals cosine of theta. So if we want to know this horizontal distance here, just like we were doing with the vertical distance before, we can just apply trig and we can use the cosine ratio to help us get this distance. So once again, if you want the location of this point, all you have to do is take a sine of this angle to get the y value, take a cosine of this angle to get the x value, and then we know the exact location of that point on the unit circle. So the xy point comes from cosine of theta and sine of theta. Key point, this is what trig, when we talk about functions, is all about right here. Okay, so let's try just a few steps. What we did with the sine function, we're going to do with the cosine. So now, if we spin an angle of 0, we have no angle. We've spun no angle, so we're still here on this axis. What is the cosine value? Well, the cosine value, again, remember, represents the x value. So what's the x value here? What's our horizontal distance here? Well, that horizontal distance is 1. And if you punch in cosine 0 degrees on your calculator, you will get an answer of 1, because we're talking about the x distance now. All right, so at an angle of 0, we know our x value is 1. And this might be strange because you're like, wait, this is a y value of 1. No, but this y value of this function is the x value on the unit circle. So it's a little confusing, but again, the function we're producing are the results, all the x values that we get as we get these different angles along the circle. Let's try another one just to see it. All right, so we're going to try another angle here. Let's see what we get. We're going to spin an angle of 30 degrees. Draw that segment there. Drop your vertical. But remember, with cosine now, it's not the vertical we're looking for. That was with sine. Now we're looking for the length of the horizontal that's created. So this one here. How long is that? Well, the way we find that is using cosine. Cosine gives us the horizontal length, right? So cosine of 30 degrees, which is adjacent side, and that works out to 0.866. So that means at 30 degrees, we have a length of 0.866. Again, don't be confused that we're showing this length this way here. Right now, when we're talking about cosine, these lengths are going to be represented this way because we're plotting them angles versus the length. Okay, so there's that one. Let's try one more. We're spinning now an angle of 60 degrees. we go to there, drop the vertical, but we don't want the vertical, we want the horizontal length because we're finding cosine. So what is the horizontal length here? Okay, run a cosine on that value, cosine of 60 degrees, we get 0.5. That means this length here on the x-axis has a length of 0.5. That makes sense because if we went all the way across, since this is a unit circle, this would have a length of 1, but now we have about half of that, so we have 0.5. So that length we're going to mark on here at 60 degrees, we got a length of 0.5, and we're drawing our cosine graph. This one I'm not going to go through all the angles like we did with sine. You're getting the idea here. Let's see what cosine looks like as we finish it. So here is all the angles along there. Cosine would look like this. We already saw it here. We saw it reaching 90. We notice it's going to go down and up again. So just like a sine curve, it's periodic. It goes up and down. It's a repeating wave. It's cyclic, but it begins at 1. Whereas sine began at 0, cosine begins at 1, because when we have an angle of 0, we have that x length of 1. All right, so there's the cosine graph. So let's see that on Desmos like we did before. All right, so here we had, before we had the sine graph, right? So there was the sine graph. There's the sine graph being created, right? Sine graph begins at 0, and it goes up and down as our y values change. See, our vertical distances, right? Our vertical distances are represented by these points. But now let's go to cosine. So you can see the cosine there. Let's wait till it starts again right here. Okay, see, cosine represents the horizontal distances, right? We begin at 1. Here's cosine values. Look, horizontal distance is negative there. And now the horizontal distance is positive. And look, positive values getting smaller. Oh, now our horizontal distance is negative. Here, negative, smaller, getting to 0. And now horizontal distance is positive again. So that's cosine curve. We have these two periodic curves now that we're familiar with. So let's go back to here and compare them. Both of them together are called sinusoidal functions. They both have the same kind of shape, so they both have the name coming from sine. You can see sine here in yellow, because at 0 it begins at 0, and cosine here in blue beginning at 1. So basically they're identical curves, but one is left-right shift of the other one. So there is our sine and our cosine graphs. These can be used to represent many real-life things. So let's look at an example now, and this is the problem we'll do together to see an application of a sinusoidal function. Together we are going to look at a Ferrous wheel problem, a very common kind of look at how cyclic functions work. So here's the situation we have. Let's say there's a new Ferrous wheel attraction at some park, and it's going to carry passengers in these pods. Safety rules require that we always know how high up a passenger is and what the angles are and so on. So let's check it out. So here's the situation. We have the radius of the Ferris wheel at the park is 70 meters. So imagine from center to one of the pods, 70 meters. And theta represents the angle measured anti-clockwise from the x-axis. All right, so imagine it's spinning, and as you get on a pod, the wheel spins this way, and the angle tells you basically what portion of the journey you've done. So first we're going to find a distance of 40 meters vertically. So it says find all the angles, which tell us we have a distance of 40 meters vertically above the x-axis. So vertically, you should be thinking y-axis. Let's take a look. So here's the diagram we can represent for that. We have our Ferris wheel. We have some angle it's spinning. And we want to know when the vertical distance is 40 meters. So we're talking about this. When is a person in a pod and they are 40 meters above the vertical here, the horizontal line? So 40 meters here. We know the radius is 70. So we've put everything we know. And we're trying to figure out what angles lead to a passenger being at this point here when they are 40 meters above here. So does that happen only once? No, it happens twice. It happens here and it happens here also. So as the person travels in the pod, they get to be here. They're 40 meters above the center. And then they travel along, go to a max point, and they come down, and now they're 40 meters above again, right? There's these two triangles. So we're looking for two angles that lead to the person being 40 meters above the axis here. Okay, so how do we solve it? I want you to just ignore the circle for a minute and just look at the triangle. We can find out that angle just using this triangle. Try it out. Okay, we can use basic trig, right? We can use the sine ratio, which brings the opposite and the hypotenuse together. So sine of angle theta equals 40 over 70. So now that you see that, can you solve for the angle? We need to use an inverse sine for that. So inverse sine gets us the angle. Solve that, and you get an angle of 34.85 degrees. That makes sense in the diagram here, 34.85 degrees. Okay, so then what does that tell us about this other angle? Try to think back when we looked at in the first video, we were looking at sine angles and saying, okay, if these two triangles are the same, then that means this angle must be the same as this one. So this angle here is also 34, but we know if we go all the way here, it's 180. So what does that tell you about the angle to get from here to here? Because that's where you need to spin to get to this pod. You spin from the beginning to here. So what do you say? All right, I hope you were thinking something like, okay, to get the second angle, I need to do 180 minus 34, because 180 spin would take us all the way to here, but then we have to do 34 less than that to end up being right here. So 180 minus 34, and that's 144.15 degrees. So again, if you're having trouble visualizing that, remember this one angle here is 34.85, and from the beginning to get to this line, that angle is this angle that we have here, 144. Okay, great. That's the kind of geometric look at it, but let's look at it in terms of trigonometry as well and graphing. So let's say we have that circle, and we can turn this circle into what we've been using, which is a unit circle. Right now this is not a unit circle because we see a radius of 70 meters. But if we can turn that radius to 1 meter, we can then graph our sine function and use that to help us. So how do you make this hypotenuse 1 meter in length or 1 unit in length? We can just divide it by 70. But if we're dividing that by 70, we have to divide this by 70 also. So if you divide both sides by 70, you're now compressing or making a similar circle, a smaller version of the same circle, with a radius of 1. So now that we have a radius of 1, we can graph it. So grab your calculator. Let's put in for y1, let's go graphing, right? So you press y equals to graph, and for y1, your first function, sine x, because we're going to graph the sine function. Okay, because why the sine function? Because we're looking for the vertical distances, right? And the sine function represents all the collection of all the vertical distances, right? So sine, and then for y2, we can put 4 over 7, because that's what happens. That is the height we're looking for. We're looking for a height of 40, but we've reduced it to 40 over 70, which actually this length then can be reduced to 4 over 7, right, if you cancel the zeros. So this length is 4 over 7. So we're going to graph the sine graph, and then we're going to graph a horizontal line at 4 over 7, and we're going to say when is the sine graph equal to that value. It might help to see the diagram for this, but before you graph that, let's set the window. When we set the window when we're graphing, remember we need the x values to show us everything. We need to see the full sine curve from 0 to 360 degrees. We want to see the pod going around all the way to 360. So set your x min to 0, your x max to 360, so that your graph knows it has to show you all the way to 360 degrees. And then for y min, let's put -2, and for y max 2. And the reason I chose that is because a sine graph goes up to a maximum of 1, down to a minimum of -1, but we're going to go just a little bit above and below that, so we see the graph fully. Okay, when you graph that, in your graphing calculator, you're going to see this on your screen. I took this from Desmos, but it should be similar to what you see. So on your calculator, you should see a sine graph, and you should see a horizontal line, which is this one, which represents this height here, right? So we're seeing when is the sine graph equal to those 2 points. And we can find that by doing the second calc and then finding the intersect. We've done that a lot of times when we model already. So second calc intersect, and you find these 2 intersecting points. And as you notice in those points, we have the same values that we had when we solved this geometrically. We have 34.85 degrees here and 145.15 degrees. You should find those 2 points. And that tells you that the y value will be 4 over 7 at those 2 angles. All right, important connections here. We'll talk more in class. Let's look at one more question. Question B says, find the distance 20 meters horizontally. So now when it's talking about the horizontal distance, it's talking about x values. And when we're talking about x values on a unit circle, we're talking about cosine. So this is the diagram to represent this. We're looking for this horizontal distance of 20. And those are the horizontal distance, which is x values. So we're going to use cosine. We're going to set it up like we did before. Cosine is adjacent over hypotenuse. Solve that using inverse cos, and you get this angle here. So this first angle is 73.4. So can you get the next angle here? Okay, like we did before, you do 180 minus that, you get that value right here. 180 minus 73 gives you the full angle to here. And now looking at it graphically, you can also graph multiple lines, divide by 70 again to make it a unit circle, graph cosine, graph the line you need, graph another one, change your window, which you already have, and there it is. We have our 2 intersection points here. However, this one has a line below and above, and that It's a little trickier, but I want you just to try it and see that our two answers are here and here. They're not going to be the two answers on one line. We can talk about more of that in the next lesson.